Welcome to This Explainer. Today, we're taking something that usually sounds pretty dense, network architecture, and turning it into a truly fascinating journey. We're going to explore exactly how data routes across the vast global internet, and we'll unpack the completely ingenious engineering that quite literally saved the entire system from collapse. If you've ever wondered how a message travels from your screen to the other side of the planet in a matter of milliseconds, well, you are absolutely in the right place. Because, the network spanning our world isn't just magic. It's a highly structured, layered system of rules known collectively as TCP/IP internetworking. These are the fundamental standards that allow vastly different devices, whether it's a smartphone in Tokyo or a server in London, to seamlessly speak a common language and form a cohesive global architecture. To guide our learning today, we'll quickly run through our agenda. First, the TCP/IP framework. Then, TCP versus UDP and the anatomy of an IP address. From there, we'll dive into the classful addressing era, the looming IP address crisis, and finally, the elegant CIDR solution. All right, let's jump right into Section 1, the TCP/IP framework. First, let's look at the broad framework handling data transmission. Data doesn't just shoot through a wire all at once, right? It moves through a strictly structured 5-layer model. This includes the physical and data link layers at the very bottom, moving up through the internet and transport layers, all the way to the application layer at the top for things like web browsing. And this brings us to a really crucial concept: packaging. Messages moving at the local level 2 data link layer are called frames, but messages at the level 3 internet layer are called packets. Within a single network, the internet layer's packets are actually encapsulated directly inside the data fields of those frames. It's exactly like putting a letter inside an envelope. The packet is the letter carrying your actual message, and the frame is the sturdy envelope carrying it securely across the local physical link. Moving on to Section 2, TCP versus UDP. Now, as we move up to layer 4, the transport layer, we run into two major protocols that have vastly different jobs: TCP and UDP. TCP is a heavyweight, connection-oriented, and strictly reliable protocol. It makes sure every single piece of data arrives in perfect order, checking and double-checking the delivery. UDP, on the other hand, is a lightweight, connectionless, and completely unreliable protocol. And by unreliable, we just mean it doesn't guarantee delivery. It just blasts the data out as fast as possible without waiting around for a receipt. You might also notice that the foundational IP protocol sitting down at layer 3 is a lot like UDP. It's connectionless, unreliable, and lightweight. And honestly, this is a brilliant design choice. By keeping layer 3 incredibly fast and simple, the network itself doesn't get bogged down. It leaves all that heavy lifting of error checking up to layer 4, allowing the entire system to scale massively. Seeing these protocols in action really shows why we absolutely need both. Because TCP is slower but highly reliable, it uses a one-to-one unicast method that is perfectly suited for web browsing, emails, and file transfers. These are situations where accuracy is everything, and a single missing byte would corrupt the whole file. But UDP's lightweight nature allows for incredibly fast, simultaneous transfers using multicast and broadcast capabilities. This best effort delivery makes UDP the absolute standard for live streaming, voice over IP, and online gaming. In those scenarios, speed matters way more than an occasional dropped frame, because let's face it, you'd much rather see a tiny visual glitch on a live stream than sit through 5 agonizing seconds of buffering. Which brings us to Section 3, Anatomy of an IP address. Let's zoom in even further to the core identifier working right alongside these protocols at the internet layer: the IP address. We hear this term all the time, right? But structurally, it is surprisingly simple. It is literally just a sequence of exactly 32 ones and zeros. That strict 32-bit long identifier string provides a unique global address for every single network interface on the entire planet. But since our human brains can't easily process or memorize 32 consecutive ones and zeros, we break them up. We divide those 32 bits into 4 clean 8-bit bytes. Then we translate them byte by byte into a standard decimal number ranging from 0 to 255. This standard translation is known as dotted decimal notation. It's how a massive, totally unreadable binary string translates organically into a much more familiar human-readable format, like 128.143.137.144. But here is where the engineering gets a bit tricky. Every IP address actually has two jobs. First, it encodes a network prefix, identifying the broader network you're on. Second, it encodes a specific host number, identifying your exact device on that network. So this leaves us faced with a vital routing question. Looking at a string of numbers, how does the system actually know where the network prefix ends and the host number begins? To find the answer, let's head into Section 4, the classful addressing era. Let's step back to the early 1980s, when internet addresses were first standardized. This era was defined by a system known as classful IP addressing. In this original system, the answer was beautifully simple by design, mostly because it was computationally really easy for primitive early hardware to process. The length of the network prefix was implicitly defined by the very first starting bits of the address itself. For instance, if a router saw an address starting with a 0, it immediately knew it was a Class A address, meaning it had exactly an 8-bit network prefix, leaving 24 bits for millions of hosts. If it started with a 1 and a 0, it was a Class B address with a 16-bit prefix. And if it started with 110, it was a Class C address with a 24-bit prefix, leaving just 8 bits for hosts. The address inherently told the router exactly how to read it.
Which perfectly sets up Section 5, the IP address crisis.
While that class system was incredibly simple and easy for early routers to process, it was basically a ticking time bomb. It caused a massive operational crisis because this two-layer hierarchy created a classic Goldilocks problem. Think about it. If a company needed, say, 300 addresses, a Class C block, which only holds about 254 hosts, was just a bit too small. So they would automatically be handed the next size up, an entire Class B block, which can hold over 65,000 hosts. That meant tens of thousands of unused IP addresses were instantly wasted and permanently locked away. Because of this mind-boggling inefficiency, huge blocks of Class A and B addresses were rapidly depleted. The internet was exploding in the 1990s, and it was quickly outgrowing the severe limitations of these rigid 32-bit classes. And that leads us to our final section, Part 6, the CIDR solution. Faced with the literal catastrophic exhaustion of usable IP addresses, network engineers had to completely restructure how addresses were assigned. They desperately needed a more granular, efficient way to hand out IP blocks. Enter CIDR, which stands for Classless Interdomain Routing. The key concept here is right in the name, classless. CIDR completely stripped away those rigid Class A, B, and C rules. Instead, it allowed the network prefix length to be entirely arbitrary. By removing the strict classes, engineers could now assign blocks of addresses that perfectly mathematically matched the exact size and network actually needed, effectively plugging the holes in a rapidly sinking ship. In practice, this flexibility uses something called CIDR notation. By simply appending a slash and the number 18 to the end of the IP address, it explicitly tells the router that exactly 18 bits are reserved for the network prefix. Because an IP address is always exactly 32 bits, this leaves exactly 14 bits hyper-efficiently assigned for hosts. There's no more guessing based on the first few bits, and absolutely no more wasting thousands of addresses in rigid, inflexible class structures. It was a remarkably elegant pivot that single-handedly saved the architecture from collapse. Now, while CIDR brilliantly saved the 32-bit IPv4 structure by maximizing its efficiency and buying us critical decades of time, the sheer scale of our modern, globally connected world is pushing those physical limits once again. The ultimate depletion of 32-bit addresses forces us to look to the final, permanent future fix, IP version 6. And that leaves us with one final provocative question to ponder. As the internet completely outgrows our 32-bit capabilities, how will the massive adoption of IP version 6 fundamentally reshape the future of global connectivity? It's certainly something to think about the next time you connect a new device. Thank you so much for joining me on this explainer, and keep exploring the incredible architecture that keeps our world connected.